I'm sure everybody did the exercise. So I have this FC mapping to C, and I have this gamma, which at the moment I'm assuming is a section, and I had n times this line bundle B is G plus M with gamma squared less than 0. Right. So you know, let's write gamma squared as minus D. Right. Then you know, I can twist the line bundle, and so I can think of that the gamma is the O of 1, or you know, in that table of what is the basis for the numerical classes for the Nernst-Severi group of the surface S. Before I had L, and I had A and L, and I can substitute A and gamma if I want to, right? And so if you do that, you'll find that B is numerically equivalent to 2 gamma plus dA. Right. So B squared is 0. You'll find if you do the if you calculate this squared, so this guy here has got degree 2 on each fiber because the gamma times the fiber is 1. And that times the fiber is 0, and this square, given this square is 0, right? So if you say, well, NB minus some multiple of gamma, let's say gamma times gamma, is, so suppose that little gamma gamma is the multiplicity occurring in here, then this thing here is this linear system does not take, so suppose this does not have gamma as base part components, then you find NB minus gamma gamma times gamma is greater than or equal to 0. Right? And you mess around for a little bit and you find that gamma is greater than n. Right. So the conclusion of the argument is, you know, we have this B. So this B for any rank 2 vector bundle over a curve, we get this fibered surface and this bundle B, which is after all just the relative tangent bundle, right? And automatically B squared equals 0. So I say, you know, if B squared is 0, then you don't really expect B to be big. If B is big, then the whole thing is unstable. There's this gamma with negative in its self-intersection, and NB has n gamma in its base locus, at least n in its base locus. Right, and you know, if you push just a little bit harder, you can get strictly greater than n there, which is really what I want. But let me just leave this for a moment. Okay, so let's go to the application. Why am I doing this basically easy material on these scrolls? Incidentally, in the inseparable case, as this gamma goes to C is bijective, but possibly purely inseparable. And then the result would be that, you know, I can still take this gamma to be a basis, I can take a rational multiple of this gamma as a basis of the rational Nernst-Severi group. And then you do the same thing and you find that every one of these linear systems has this gamma to some multiplicity, so that multiplicity times the fiber is greater than n. So, you know, it's p to the n times whatever multiple of gamma it is, but it's still the product p to the n times the number of times gamma appears there is greater than this n. So you know, I mean, historically, you know, if I've got p1 and I've got a polynomial, if I've got f of x1, x2 of degree 2n, right, then we say he's unstable if f2n has a root of multiplicity greater than n. So let me just sort of say history and culture for 1 second, right? That means if you know, so if the guy, for example, is x1 to the power of n times x2 to the power of n, has two roots of multiplicity exactly equal to n, then we allow that as semi-stable, right? So the thing that we don't allow, so this is strictly unstable. Right, and very, very roughly, I'm not going to try to justify what I say, but you know, if I have a matrix M, if I have a 2n by 2n matrix, and I have a block like this of size greater than n times n, right, then automatically determinant of M is 0. Right, so this is the kind of spirit in which we're doing this. There's this theory called geometric invariant theory. You know, I'm not going to go into it, but the kind of thing that's happening here is this instability. Here I've got this idea that there's one root, in this case the thing corresponding to the curve gamma, and that's appearing at least n times in every as a root of every polynomial here. Right? And so, you know, this is basically the same kind of thing. You can relate these things if you want to. This is Hilbert's Mumford. Right, and it was also the original proof of Bogomolov. Although the proof I'm giving here is, of course, much, much simpler. Okay. So, you know, I mean, you know, corollary or sort of obvious extension of the result. If I've got if I've got X projective scheme, irreducible projective scheme, and I've got E, a rank 2 vector bundle on X, and suppose that, let's say of dimension greater than or equal to 2, I've got a rank 2 vector bundle on E, and write B for O of 2 tensor determinant of E to the minus 1 on P x P. Right? So this is this proj thing I've been talking about. Right? So if B is big, then there exists a section, there exists a quasi-section y inside this px of E. So this is all over x. And so this one here is generically, so this is generically bijective. Oh, it's inseparable over the generic point if you want. It's generically bijective. And NB has NY as base part. So I'm, of course, or, you know, n over p to the n if it's inseparable of degree p to the n. Okay, so the proof, the only thing I'm saying is I'm assuming that B is big. So B is moving around in some multiple of B moves around in some big linear system on this P of x. So take any curve C in x, or any curve C mapping to x, and then take the pullback PC of E, right, and then just apply these arguments I've been doing there. Right? The fiber, you know, this x might be singular, might be non-normal, and so on. The curve C might be mapping to x, not exactly an isomorphism, but that doesn't really matter. The statements I'm making here about the generic fiber of x are something that you only measure on the fibers of the map. And the fibers of this map and the fibers of this map, however bad the map is, are just the same. Right, so this is just a pull back diagram. Right, and so you get out this. So I'm going to apply this with X and non-singular surface, but first of all I need to understand how we can get this how we can get this conclusion. So the theorem, so this is Bogomolov instability. So it's this. So S non-singular surface, characteristic 0, E rank 2 vector bundle, then C1 squared minus 4C2 of E is greater than 0. I'm going to explain just a little bit about what C2 is and how you calculate it and so on, so don't despair if you haven't seen it. If and only if. There exists a sequence O goes to OS of L, short exact sequence, goes to E, goes to I of some zero-dimensional scheme, Z times OS of M, goes to 0, right? Short exact sequence. With one part of this is easy. L minus M squared is greater than degree of Z. Right, and so you will see, when we do the calculation, we'll see that this condition here is just calculating this number. So if I have any short exact sequence like this, it will satisfy this condition. Right, but that's not the point. Is not that. The point is that L minus M is big. Right, or if you want, that L minus M times H ample is greater than 0. Right, so this guy L minus M here is just some divisor on the surface. So if L minus M squared is 0, it means either some large multiple of L is positive or some large multiple of minus it is positive. And so if some large multiple of this is negative, if this L is very, very small and this M is very, very big, then there's nothing special about that. You can always make sequences like that. Right? But the point is we can do it where this L here is bigger than 1/2 of E. Right? This is saying there's an L and an M here. L plus M is the first Chern class of E. And this condition is saying that L is greater than M. So L is greater than 1/2 of the degree of E. Yeah? And so this is unstable. This is the thing that's unusual and very special about a vector bundle. Okay. Okay, so let's first of all understand how to calculate Chern classes. So, you know, there is a formalism of Chern classes. So, Chern classes. I told you one of the games that you play of vector bundles. So I told you earlier this Grothendieck definition of the Chern classes of a vector bundle. So you go to this P of the bundle. That's a place where there's an O of 1. So the O of 1 is sort of splitting off one little line bundle out of the vector bundle. And then you do the formal calculation I did, and that tells you the definition of the vector bundle. But now I'm going to tell you something which is much more useful, which is how to calculate with it. So, you know, I want to know, for example, when I've got this situation, when I've got this OL goes to E, goes to IZ, OM. Right. How do we, so this Z is zero-dimensional. I'll explain what the sequence means at the near Z in just a minute. Right? So how do we calculate? How do we calculate C1, C2 of E? Right? And so, you know, how do I say this? So C1 is L plus M. So, you know, the L and the M are divisors. And so the L and the M, I'm really thinking of them as in pick of S. Right? And then I'm using the same letter for C1 of L and C1 of M in H2 of S Z. So if I want to think of them as numbers, and that one C1 squared minus 4C2 is about numbers, then I go to cohomology and I calculate that. Right? And C2. So, you know, we could pretend that we don't know what C2 is, or we could say, well, C2 is clearly something like L times M plus Z. Right? So how can we determine? So what we do is this, and this calculation turns up again and again and again, and I'm going to use it later. So I've got E. I want to calculate something. So what we do is this. We pretend that E is alpha direct sum beta, where alpha and beta are line bundles. Right, then we say, then C1 of E is alpha plus beta, and C2 of E is alpha times beta. And if it were a vector bundle of rank n, I'd write here alpha 1, alpha 2, alpha n, and call these the Chern roots of E. And then I would write down here not just alpha plus beta and alpha beta, I'd write down all the elementary symmetric functions in alpha 1 up to alpha n. So alpha plus beta and alpha beta, there are the Chern roots. So if I take this sequence, tensor O S of minus L, right, then I get O goes to O S goes to E tensor minus L goes to O S of goes to I Z of O S of M minus L. Okay. So this Z, so this guy here is this is OS, and this guy here is everywhere locally. This is locally, everywhere locally isomorphic to O plus O. Yeah. So a homomorphism between these is a 1 by 2 matrix that I can write like this: S1, S2. So S1, S2 are just functions on S. Locally regular functions on S. Right? So if S1 and S2 don't have any common zeros, then I can take one of them to be a basis of one of these. I can change this direct sum decomposition and take one of them to be the basis. Right? So the problem comes where S1 and S2 are both 0, right? Then there's a zero scheme, Z S1 S2, and that's the ideal generated by S1 S2 in OS, right? And so this is the ideal of Z. Right, and then locally, this sequence is, we know what this sequence is. The sequence is S2 minus S1, goes to IZ, goes to this line bundle. Right, in other words, this sequence here, the thing I've written down here, is the Koszul complex of the irregular sequence S1, S2. So to say that S1 and S2 don't have any common factors means is the same thing as saying they form a regular sequence. So they define a codimension 2 complete intersection. They define a zero-dimensional ideal. Right? And so in any case, I'm assuming here that I have this sequence and the kernel here is only different from, you know, I mean, there's no torsion in the kernel. So there's this little thing that happens in codimension 2, but nothing at all happens in codimension 1. So the conclusion of this is that C2 of E tensor minus L is just the degree of Z. Yes? So that's if you want the definition of C2. C2 of a vector bundle is, C2 of this vector bundle is the number of zeros of a general section, assuming that it's got lots of sections that vanish here only in codimension 2. Right? So if you want to, you can take this as a different definition of C2. Right? But then if we know that, then how do we calculate C2? Sorry. So, you know, assuming we know this, then how do we calculate, how do we go from this thing here to C2 of E? Right. So this guy here, as I explained, is we think of E as being alpha plus beta. Right? We pretend that he's a direct sum of two line bundles. Right? And then E tensor minus L is alpha tensor minus L. Let me just write. It's the line bundle alpha, OS of alpha minus L, direct sum OS of beta minus L. Right? And the Chern classes of this are that this has Chern classes alpha plus beta minus 2L. This is C1. C2 is alpha minus L times beta minus L. Right, so this is alpha beta, which is just the C2 of E. That's the thing we want. And then minus L times A plus B plus L squared. Right, so that's how to go. You go from C2 of one line bundle to C2 of the same bundle of the bundle twisted by L. Right, so alpha beta C2 of E itself is C2. C2 of this is the degree of Z. This guy here is the C2 of E minus L. Right, that's star. Right, that's this term here. And then minus, so it's L times alpha plus beta, but we know alpha times beta is. So alpha times, anyway. So this is L times L plus M plus L squared. Okay, anyway, I'm getting fed up with this. So I should. Right, what are we? What's the conclusion I want to come to? So the conclusion I want to come to, which I seem to have got slightly screwed up at the moment, is that if I have this sequence, 0 goes to OS of L, goes to E, goes to degree of, goes to IZ times OS of M, then L minus M squared is C1 squared minus 4C2 of E plus degree by Z. Right. So, I mean, you know, this is just a calculation. I mean, maybe I haven't said it exactly right, but it's easy to get. It's easy to get to that using exactly the same ideas. Right. So here, C1, C2, C1 plus C2. Sorry, L plus M is C1, and C2 is something that I calculated here, possibly slightly wrong. Right. So C2 is degree of Z. And then possibly plus, you know, L squared and M squared and L minus M squared. Sorry?
Plus LM.
Plus LM. Thank you.
The computer did that.
Right. Yes, yes. Yes, I confused myself. Okay, so, you know, if I do L plus, if I want to calculate L minus M squared, this is the same thing as L plus M squared minus 4LM. Right, and so these are the terms appearing here. And maybe there should be a 4 there. Anyway, I'm not going to worry about this anymore. So, you know, this condition here only, sorry, this condition here and any sequence here implies this. So why on earth does there exist a sequence with L and M, with L bigger than M? Okay, so now I have to do this Riemann-Roch thing. So, so now let me take B. So of course I'm going to go back to my, my P of E. So I'm over S. I've got this vector bundle E. Later on I'm going to be assuming that C1 squared minus 4C2 is greater than 0. Right? And I define this B. So B is exactly the same thing as I've always had, O of 2, OP E of 2, tensor the pullback of determinant of E to the minus sign. Yes?
You need the 4.
4.
Degree.
Yes. Thank you. Yes. So what am I going to do with this? And what's it got to do with... So this is a line bundle on a threefold, PE. So one idea would be to write out Riemann-Roch on a threefold for H naught of n times B. Right. An alternative, which is what we're actually going to do, is take the line bundle OPE of n times B. Right. So what happens when I push this down? Well, when we push this down, I'm going to get I'm going to get the push down of O of 2n. Which we know is sim 2n of E. And then say at some point we say the projection formula, say taking the push, doing this, tensoring by this pull-up and pushing down, we might as well do the tensoring by the pull-up down afterwards. So this is tensor determinant of E to the minus n. Sorry, I've changed from big N to little n. Okay, so this bundle has large degree on the fibers. And so there's no question of there being any R1 pi lower star. Right? R1 pi lower star is 0, and it's 0 after pullback, and it's 0 at every stage. So well, I can use coherent base change theorem to say that this is a sheaf that we can calculate fiber by fiber, and it is just what I said. Right? So, you know, what have I got here? Well, you know, these are symmetric tensors on E. So, you know, if E is O x1 plus x2, right, the thing I've got is polynomials in x1, x2 of degree 2n divided by xy, x1, x2 to the power of n. Right. So the thing I'm writing down here is sort of basically kind of has got this kind of neutral property. It doesn't depend on, you know, it depends. There's some kind of determinant going on here, which is the trivial bundle. So in fact, this is a bundle of rank 2n plus 1, but its determinant is the trivial bundle. So the claim is that H naught of this guy if C1 squared minus 4C2 of E is greater than 0, then H naught of this bundle tensor determinant E to the minus n. So this is the bundle that's got sort of trivial determinant. Grows greater than a positive constant, a constant greater than 0 times n squared. And I'm going to have to worry that I don't mean n cubed. But anyway, it grows. It's going to grow like anything. Right, and so you know, this is I'm going to have some kind of I'm going to have to work to establish this point here. But why do I want this point? I want to say that this B is big. Right, so the H naught of this bundle here is the same thing as the H naught of n times this B up on the threefold. Right. So I've got this bundle on the, so B. So that you know, when I've finished doing this argument, which is sort of basically just Riemann rock and a bit of messing around. So B on PE. I'm sorry, I want this n cubed. Is big. Right. However, for every curve C in S, B squared times the surface FC is 0. Right? So I've got this thing now over X, PE. Right? One-dimensional fibers. And then if I take any curve C in X, I can restrict this down to the FC I was talking about before. I've got a line bundle here, B, which is big on the threefold. So it moves in a, you know, arbitrarily large linear system on the threefold. However, when I restrict it down to any of these surfaces, it's got B squared equals 0. And so, you know, I can choose the curve C to be fairly general so that it's not contained in any vertical parts of the base locus of B. And then the conclusion is that as far as this curve is concerned, this bundle here is unstable. There's a section in here there's a section in here so that every section of this big linear system vanishes with multiplicity greater than n, greater than or equal to every section of this bundle which has got degree 2n on the fibre vanishes on this section with multiplicity greater than n. So at least 1/2 of its vanishing happens along one section. Right? And so the conclusion is there's a y in there. Right? And this restricting to this y provides the kernel of this map. Okay? So the main thing I have to prove here is this. And so, what are we going to do? Well, obviously we're going to ask Riemann Roch, does Riemann Roch know anything about this? Right? And Riemann Roch is going to tell us that H0 plus H2 of that bundle grows. And, sometimes it often happens in the theory of surfaces that you want the H0 to grow and therefore the H2 cannot grow. In this case, they're both growing it, and they're both growing at around the same speed. The point is to show that this growth is at least half of the growth goes into the H0. Right? So, I can't remember how I'm going to do this. So H0 of sim n e tensor determinant sim 2n e sim 2n e times determinant e to the minus n. Okay, so the first thing we're going to do is ask Riemann Roch. Does Riemann Roch know anything about this? K of s and this going. So how are we going to calculate this? So this is a rank 2n plus 1 vector bundle over S. So what can we do with it? Well, I said earlier that what we're going to do is, when I've got to calculate anything to do with a vector bundle, what I do is pretend that E is alpha plus beta. Right? Do some calculation with alpha and beta. At the end of the calculation, we'll have an expression which is symmetric in alpha and beta. Therefore, it can be expressed as functions of the elementary symmetric functions of alpha and beta, which is alpha, beta, and which is exactly the same as here. So I'm sorry, I didn't give this a name. This pretending is called the splitting principle. Right? And I'm not doing anything dishonest here. Right? This is genuine mathematics because it is always possible to make a tower of varieties, one over the next, so that on the top variety the splitting principle holds, that the splitting actually holds literally, and the pi upper star maps as you go up and up this tower of varieties are all injective, right? So you're supposed to do this pretense and then say, right, well, it's the thing I've done is rigorous, although I'm doing this pretense. Okay, so look, I don't have time to do this. So apply this to Riemann Roch for the sim 2n e tensor determinant e to the minus n. So what do we have to do? So if E is alpha plus beta, then sim 2n of E is 2. So I don't know whether to use multiplicative or additive notation. I think I'm going to use additive notation. No, that's better. It's better to say this is OS of 2n alpha plus OS of 2n minus 1 alpha plus beta plus, I think you get the idea, So this is the direct sum of O S of, let me say, A alpha plus B beta with A plus B equals 2n. Okay? So, so if this were alpha plus beta, then polynomials of degree n in the E are polynomials of some degree in the alpha part plus times polynomials of the complementary degree in the beta. Right? And then I have to, if I want to tensor back down with this determinant of beta minus 1, right? What I'm going to do, now I'm going to do minus n alpha plus beta to each of these terms. So when I do it here, you see very clearly what's happening. I'm doing 2n alpha plus beta, and then I'm doing minus n times alpha plus beta. Right? So the thing I'm getting here is n times alpha minus beta. Right? And we had this calculation time and time again. Alpha minus beta. I'm going to do alpha minus beta squared. This is alpha plus beta squared minus 4 alpha beta. Right? This is exactly the discriminant. Yeah? And so what I'm getting here, what I'm going to get is a sum of 2n plus 1 terms, each of which involves this discriminant to some degree or other. Okay, so you know, I've sort of said, I've described how the calculation is going to go. Now let's try to do it. Right. So the thing I've said is, I take this vector bundle E, rank 2 vector bundle. Let's pretend it's a direct sum of 2 line bundles. When I do this n symmetric power, this is the symmetric power here, and then twisted back down to get. So I'm going to get so if I'm going to do chi of S and the thing I had before, that sim 2n of E tensor determinant minus n. Right. So this is chi of something which we can pretend is a direct sum of line bundles. Yes. So this is direct sum from n from. Let me do it as I did before. A plus B equals 2n. And so what am I going to get? I'm going to get chi of A alpha plus B beta minus n A alpha plus beta. Right. So it's better to write this as a sum of A what am I supposed to say? This is sum of chi of. So the thing that's appearing here is it's n alpha minus beta, and then it's plus n minus 1 alpha minus beta, and then it's plus, and so on, plus I times alpha plus beta. Okay, so it's a sum for I in the range minus n up to plus n. Right, there are 2n plus 1 terms here, and it's I times alpha plus beta, alpha minus beta. Right, and so you know, I'm sort of pretending that I can deal with these as if they were just sheaves over S. So that's the splitting principle. Right. So what do I have to do for this? Well, I have to do Riemann-Roch, and so this is n plus 1 copies, 2n plus 1 copies of chi of OS, right? And that's, so the, you know, we're looking for the term which grows of order cubic in n, and so that's not this term. And then there's plus, so what else is there in there? So I'm supposed to do sum, the same I, in this same range, minus n to plus n, of, so this is I alpha minus beta times I alpha minus beta minus ks divided by 2. Okay, so the only thing I've done there is writing, the only thing I've had to do there is writing down the Riemann-Roch theorem for a line bundle, admittedly a kind of pretend line bundle. Yeah, so in there there's alpha minus beta squared summed, so it's, you know, there's a half somewhere here. The sum over these values I in minus n to plus n, right? Well, in fact, you know, the alpha minus beta, this is just, so there's a half coming out there, and there's alpha minus beta squared there, and then there's some I squared for I in this range, minus n to n. Right, so that's this term, ignoring the ks. And then there's minus ks, and then there's that times sum of I in the range I in minus n to n. Right, and this is a very happy sum. Right, this one is 0. Right, because every term appears there once positively and once negatively. And so, you know, who is this? Who is this? So, you know, because I'm seeing this I squared there, there's not going to be any cancellation. Each of these terms is positive, whether the I is positive or negative. Right? So the thing I'm getting there is C1 squared minus 4C2 times n cubed times a constant. Okay, so there's a, you know, this is the sum of I squared from I equals 0 up to n, and then it's twice that, so that just cancels that. So I think everybody knows the sum of n squared, the sum of I squared for I equals 1 up to n is something like a cubic. So it's just, it's like I cubed over 3. It's the same as the integral. Right? So there's n, something like n cubed over 3 or n cubed over 6, it doesn't really matter, right, times this constant term here, which is constant because it's the discriminant alpha minus beta squared, and then times some other constant, which, well, I think it's actually that. Okay, so it's this plus lower order terms. So it grows like n cubed times positive constant. Okay, so, you know, this is a sort of messy place. The result I'm trying to prove is very coarse. I'm just trying to prove that this B moves around on the threefold. Right, that this B is a big linear system. And, you know, for some reason or other, we have to go through this rigmarole of saying, you know, I'm doing Riemann-Roch I'm really doing implicitly Riemann-Roch on the threefold. Okay, so that's one part of the calculation. There's another part of the calculation, which is to say, you know, there's an so this proves that H naught of this guy. So it's H naught on the threefold P E X of this n times b plus h2 of the same thing, n times b, right, the sum of these is greater than or equal to n cubed over times constant for n. Yeah, so we haven't completely finished. We haven't, there is something there that's growing, but it will be a disaster if it's only the H2. So there's a second part to this. There's a second part to this saying that H naught of this bundle here, if I do, so the one I'm worried about is H2 of sim 2n e tensor e determinant e to the minus 1. Right, so it turns out that this is the same thing. So if I write H2 here for the dimension, this is the same thing as H naught of sim 2n e tensor determinant of e to the minus 1. Right, so what do I mean by that? Twiddles, I mean the difference between the two sides. In absolute value is bounded by a constant times n squared. Okay, so you know, this is powerful, but it's not very pretty. It's a sort of messy argument. I've thought about this over a very long period of time. There's sort of some way of making this really clean, but I don't know. Right, so why is this? So, you know, one little thing that we should have noticed at the beginning is E is a rank 2 vector bundle. Right, so there's this wedge 2 of E is determinant of E. Right, but in this context, I've got E tensor E maps to wedge 2 of E, the skew symmetrizer. Right, and this map is this is a perfect pairing. Right, so in characteristic not equal to 2. I'm not going to try to tell you what happens in characteristic 2 because it's one of these things that my former student Nick Shepherd Barron will try to frighten people with. So the conclusion of this is, you know, this is general culture. E dual is the same thing as, so this is hum, of course, hum, curly hum of E OS. It's the same thing as E tensor wedge 2 of E to the minus 1. Right, so the conclusion is that, so, you know, I mean, what do I want to say? When I do this sim 2n of E, tensor determinant E to the minus n, this is also self-dual. Right. So when I do H2 of him, that's the same thing as H naught of, I take the dual of that bundle, and then what am I supposed to do? Tensor omega, tensor OS of KS. Right? This is just their duality. Right? But this bundle is self-dual. So this is the same bundle. Right, and so this statement that the two are growing at more or less the same speed is just the same as saying, well, let's take this Ks, let's write K as ample divisor minus ample divisor B, and then say, well, I can take all of the sections there and restrict them to the A, and then so make them vanish on A, then allow them to have poles on B, and the only thing we're doing is changing the sheaf along curves. And so that's why you get only this less than constant n squared. So, so it's because in H0, and H1. Okay, so so you know, this is a messy argument, and I'm not saying it completely correctly in any case. Okay, so so next time I want to say that so you know, everybody's taken notes of the fact this is the first day after the Christmas holidays, after the New Year holidays for you. I'm back here on Wednesday, February the 17th, and I'll be giving a lecture. So next time I'll be talking about the following thing, that Bogomolov, I'll try to tidy up Bogomolov instability a bit. So this Bogomolov instability implies Kadara vanishing, and it also implies most of Bombieri embedding. So you know, there's a little bit of mess there as well. I mean, there's this you know, you can prove that it separates points, but you can't prove that it separates tangent directions at -2 cycles. So it's you know, this is the interest of this is technical. You know, we're doing lots of things in cohomology and bundles and restrictions of bundles and so on, writing down exact sequences and calculating stuff that everybody has to know in order to be a good algebraic geometer. Well, you could wait till next Wednesday. As I said, this Bogomolov instability does not work in characteristic P. It does not work because the kind of instability you get is there is this quasi-section which may be purely inseparable, right? And so it tells you something like any of these cohomology classes are killed by taking a suitable pullback by Frobenius maps, right? But so what? I mean, that's not strong. So you know, how could you make this? How could you try to make this argument work in, for example, in large characteristic? Right. So there was all of this stuff about these sections growing. Right. I don't actually need all that many sections. So if I have, if H0, if there exists an n, such that this H0 of this sim, whatever it is, 2n, you know, this bundles I've been talking about all the time, if this is greater than 2n plus 1, then the argument works. Right? Because I can take all those sections and I can force them to be 0 on one particular fiber. Right? And then I can take only surfaces passing through that point, only curves passing through that point, and I get instability there. Right? And so, you know, if your surface has reasonable small invariance, then you will get this for n quite small, right, without having to say let n go to infinity. You'll get this n quite soon, and then it'll be true for, you know, you can't have inseparable maps of degree smaller than that n. But, you know, that's not a very good result. So, look, if you're really interested in surfaces in characteristic P, you should read what Nick Shepherd-Barron and what's his name, Eckerdal have to say. You know, because they're doing really, really substantial things. I mean, you're asking basically questions out of curiosity rather than, you know, serious research questions. I'm not. So you know, this is not the right way to do Kadara vanishing in characteristic P. Whereas, you know, Shepherd-Barron, for example, does have correct methods of doing, you know, the equivalent of Kadara vanishing in characteristic P. Yeah. So, you know, I'm sorry, you know, my experience of algebraic geometry is that, you know, you work in characteristic 0 when it's convenient. So, you know, of course, I'm perfectly well aware of these inseparable phenomena and so on, but, you know, if it means a lot of extra work, I'm not going to be doing it. I'm not going to bother. Okay? So, you know, there's lots of, there's room in the world for lots of different people. I'm not objecting to other people doing it.